Hi, I'm Mitch Hangay from Revolution Computing, and today I'm going to be talking about extending the 16 general purpose register standard beyond RV32E. So before I begin, for those in the audience who don't know, RV32E is the subset of RISC-V intended for deeply embedded microcontrollers, and it makes a large number of simplifying assumptions, primarily of which it, sorry, give me a second, it reduces the architecture register file size from 32 to 16 registers, and forbids the use of various ISA extensions such as floating point registers. So the point of today's talk is primarily going to be motivating that there actually are other markets that actually can benefit from reducing the number of architecture registers, and that really the 16 general purpose register standard should be made orthogonal, just like all the other RISC-V ISA extensions. So, what is the motivation behind this? In general, register file area, power, and latency is key to design of any, microprocessor. In terms of the embedded space, microcontrollers like RV32 are targeting are obviously much more concerned with area, but even at the high performance perspective, so, heavily multi-thread out-of-order CPUs, power and latency are critical of the register file for their design. And in fact, if you look at modern out-of-order CPUs, more than 20% of total core power are actually dedicated towards register file access. And this has really been exacerbated by industry's move to kind of non-custom, fully synthesizable designs. And so now that we're in the era where basically wide issue out-of-order processors are common in these synthesizable designs, we're basically forced to flop-based register files. And anything you do to reduce the actual area for registers tends to actually better designs. Additionally, large register files have historically helped better with static code scheduling. So if you have a simple in-order processor such as Rocket, or say a high-performance VLIW, it can be great. However, modern wide-issue out-of-order processors are now becoming ubiquitous. They're no longer in the domains of just high-end mobile phones or servers. They're deeply embedded in our networking and storage stacks. And so modern wide-issue out-of-orders have the ability to, one, hide the actual penalties from reduced architecture register files in terms of hiding the additional bandwidth for spills, as well as hiding their latency by looking ahead in the instruction stream. And so, the relative benefit of more than 16 registers is actually relatively debated. You can find public quotes from former AMD architect Mitch Alsop talking about how, they had actually looked at 32 registers for x86 when they moved to 64 bits, and they only saw about a 3% benefit from doing so over 16. And, obviously, register usage is relatively asymmetric. Very few architecture registers comprise the majority of accesses based upon just calling conventions and code scheduling. So, what if we actually made the compiler aware of this and actually had an out-of-order CPU? Would we really see a large performance degradation? And that's part of what this talk is to basically investigate. Additionally, there actually is market demand for basically floating point capable cores with reduced architecture register files. So, NVIDIA with their Tegra 2 and ARM Cortex-A9, they actually elected not to use ARM's full 32 double precision floating point registers and actually used a half 16 register subset. In fact, if you actually look at what ARM offers from microcontrollers, it's about a third of their current cores, half of the floating point capable ones, actually don't support the full 32 double precision floating point registers. And so, in addition to that, whatever architecture state you have to maintain per thread, kind of affects the efficiency of a core. So if you want to implement heavily multi-thread designs, the actual architecture that you have to maintain is a large thing. So if you want to implement, say, a 8-threaded CPU, with RISC-V, you're basically looking at 256 registers, architected registers, versus 128. You can physically build 128 architected register multi-thread CPU. It's a burden, but you can do it. But once you get to 256, that overhead becomes kind of untenable. And so finally, related to this in a bit, the overheads actually end up not being that great because by actually having the architecture register files, you often end up reducing the call and interrupt overheads. And actually, because of the way the RISC-V compressed instructions at ISA is, you actually tend to get better use of the compressed instructions. And so our general ask is basically, why not make this standard just orthogonal like the other ISA variants? So what's our methodology? So basically, we just kind of lopped off, just like RV32E, the upper half of the register file. So we only have X0 through X15, as well as F0 through F15. So the calling conventions are mostly unmodified. I wasn't notified about the ISA naming convention, so we're calling it RV64R for this, which just stands for reduced. And we just modified the development branches of GCC and glibc. We used the Gem5 simulator, so we simulated both an in-order CPU, kind of approximate perf of an ARM Cortex-A8, and an out-of-order CPU of about approximate performance of an ARM Cortex-A57. We ran a variety of simple benchmarks, core mark, drystone, whetstone, as well as a reduced input subset of spec. So what do we see with this? So, and generally, if you look at static code size, we see anywhere between a 6 to 8% increase in static code size just because of additional spills in the code. If we look at dynamic instructions, we actually see a lesser increase in terms of dynamic instructions relative to the actual static code size. And so here you can see, core mark had 5% more instructions, drystone had 5% more instructions, core mark had 2%, and more interesting is whetstone actually got a reduction. This is actually due to calling overhead. If you actually look at the instruction mix profile, the only difference is that whetstone actually had fewer loads and stores. And so all more interesting is also all these benchmarks were compiled with O2. We actually ended up changing, so GCC uses a variety of heuristics of whether it should inline a function or not. Here on whetstone, we also got about 4% fewer dynamic function calls because the GCC more often chose to inline a function based upon its heuristics. In terms of dynamic instruction bytes, we're actually disallowing the upper registers, and so we actually tend to, by forcing the compiler to allocate lower registers, getting better utilization of compressed instructions. If you actually look down to execution time, so here drystone was the one benchmark that was negatively impacted, and it's more or less on the in-order core, got hurt by about 5%. However, all other benchmarks basically were not degrading performance, and our out-of-order CPU actually had 8% better performance counterintuitively by having an architected register file. So, okay, those are relatively simple benchmarks. What does it look like on spec? So here's just static code size. So in general, the static code size ranges anywhere between 4 and 8% static code size increases. On average, the increase is about 6%, slightly more for FP than integer. How does this relate to actual performance in spec? So here, looking at the overall average results, on average, we got about 0.5% more instructions, but we actually end up getting better code density, execution time on an in-order CPU, and our out-of-order CPU by just over slightly a percent. So this is kind of a counterintuitive result that we have the architecture register file, but we actually are getting better performance. So drilling in, on kind of the two most interesting benchmarks, so PerlBench and OmniTPP were two of the benchmarks that actually got a reasonable speed up from doing this. And this seems to be primarily related, again, to basically function call overhead. So we have fewer call or save registers. And so these were the two spec benchmarks that actually have the highest call frequency, calling a function every 35 and 23 instructions respectively. Additionally, PerlBench was managed to actually have fewer function calls because it ended up doing slightly more inlining. Can I kind of highlight how GCC's heuristics are actually greatly changes? So here, the data for MCF doesn't look that interesting. Slightly more instructions, no real performance difference. However, if you actually look at the basic instruction mix breakdown, it had about 29% fewer dynamic instruction calls, or dynamic function calls, because of inlining. So how does FP look? So integer was not hurt, but FP actually was. So in general, on FP, we saw about a 12% increase in dynamic instructions, 6% increase in dynamic instruction bytes, and about a 4.5 to 5% increase of execution time for the in-order and out-of-order CPUs. If you note here, one benchmark was by far worse than all the other ones. And this is basically GCC's register allocator completely failed on this benchmark. And this actually seems to be something that's relatively known because x86-64 also only has 16 floating point registers. And you can find academic literature documenting how LLVM's register allocator typically fails in this benchmark as well at various times. And so the code can be scheduled with 16 registers. It's just traditionally it will perform very poorly. So, what's our motivation behind this? So our motivation primarily is really based on multi-thread out-of-order designs. And so, effectively register file size for a high-performance out-of-order CPU is the equation of, how many general purpose registers you have, how many threads you're going to have, and what instructions and window size are you targeting. So it makes no real sense if you have a very heavy thread context to put it on a very small instruction window size. And so it kind of limits the scope of, when does multi-threading actually make sense for a given design. And so, there's limited designs examples in the market. You can actually look and see various ones. One of the best examples is kind of the IBM Power 4 to Power 5. By adding SMT, they increased the register file size by 50%. And so someone asked a very interesting question. A prof at Berkeley said, why did they only go 2 threads? Why not 4? And they very intelligently highlighted that basically the actual amount of physical register they'd have to increase to that would be problematic. Luckily, since the date this lecture was given, IBM's released the IBM Power 8 with 4 threads, And you can kind of see what their choice was to support, 256 registers in a primary register file. And their decision was, or 120 in a primary register file, and their decision was they didn't. They effectively ended up using register caching and only supported 16 architected registers per thread in their main register file. And so I can get into it after the talk, but effectively, once you have to go to register caching, you basically negate any of the benefits of having a larger architected register file. So, what designs are we thinking of? Basically, if you're thinking of a small out-of-order window CPU, it's currently impractical if you were to use an ISA like RISC-V or ARM due to the number of registers they require if you have only perhaps a 20 instruction window, because the amount of growth you require in your main register file size would negate the benefits in terms of energy per access to your main register file. So for basically integer-based storage and networking workloads, which do have ILP but have long latency misevents, this would actually be a beneficial ability to reduce the architecture register file size. Additionally, as I mentioned, if you want to build a high, heavily multi-threaded out-of-order CPU, if you want to support 4 or 8 threads without having to resort to things like register caching, you really don't have an option unless you actually have slightly fewer state, because the overheads to actually do this access will actually grow too much. And so, luckily I'm on time, so hopefully I was managed to highlight kind of the market forces behind this and demonstrate the actual impacts of reducing the RISC-V architecture file size for both Azure and FP workloads. We saw Azure largely wasn't impacted, and FP had about a 5% performance degradation. Additionally, it has some interesting impacts, suggesting that perhaps the current RISC-V calling conventions are a little heavyweight, since we actually got better performance, and GCC's inline heuristics are very heavily and easily influenced. Thanks, and that's my talk. Oh.